All right, my name is Phil White. I'm the CTO of Scale Computing, and today I'm going to talk about high-performance block storage with Scribe. But before I do that, since this is our first OpenStack Summit, one thing I'd like to do is give a little bit of background on Scale Computing, who we are, and why we're here today. Scale was founded about 10 years ago, and the goal of the founding team was really to sort of solve infrastructure for small and mid-sized businesses. Because as it turns out, it's challenging to set up virtualization and storage correctly and do that in an inexpensive way. So here we are 10 years later. Our primary product is HC3, which is depicted here. It's an infrastructure appliance. And what we've done is really just sort of unparalleled in the industry as far as the level of automation and orchestration we've put into these boxes. And so you're literally from unboxing to deploying virtual machines in under 30 minutes. And that's kind of been the goal. But you can ask, why are we here at OpenStack? And well, the answer is simple. Much like OpenStack, internally in our product, things are very modular, and we've got some interesting compatibilities with the OpenStack ecosystem. In particular, our storage stack, which we call Scribe, is extremely high performance and is compatible with QEMU KVM. So we're going to talk a little bit about that today. What we can do with Scribe is separating this out from our product and using it as a standalone software-defined storage product and integrating that with OpenStack is kind of what we're announcing today. So we will be able to support Scribe using a Cinder driver as a standalone, high-performance, software-defined storage stack. So let's talk a little bit more about Scribe then specifically. What Scribe really is as software-defined storage is it aggregates the block devices that are directly attached to all of the nodes in your cluster, whether they're NVMe or SATA or SAS SSD or spinning disk, into a single pool of blocks that is consumed by guest VMs in the system. So whether those synthesized virtual block devices are all on NVMe or all on SATA or SAS SSD or on spinning disk, it doesn't matter. Scribe is intelligent enough to figure out where those blocks belong based on patterns of access, et cetera. So what we're doing by pooling all these devices together is we're able to implement in software the tiering and the data protection and efficiency that you don't have to then worry about inside the guest VM. So key features and attributes of Scribe, and honestly, most of these are table stakes for a software-defined storage solution. We're targeting the QEMU KVM virtual machines. We've done a lot of optimizations around that. Thin provisioning, obviously important in a virtual environment. You want to be able to over-provision your storage if you want to. If you say have a 2 terabyte virtual volume that maybe only is using 10 or 100 gigabytes of physical space, thin provisioning is important for that. High availability also goes without saying. If you lose a drive or you lose a node in your cluster, you want that virtual volume to remain available and be able to bring it back up on another node or keep it online in the case of a drive failure. And when those failures occur, you want to be able to recover online. You want the system to restore the reliability that you had prior to the failure, and you want it to happen in the background without even knowing about it. We support snapshots and clones up to 5,000 snaps per virtual volume, as well as instant cloning from those snapshots into additional writable volumes. We support live migration from node to node of virtual devices and VMs. I mentioned tiering already. We're able to intelligently identify hot and cold blocks and put them on the appropriate tier of storage. Asynchronous replication for disaster recovery is also supported. If you lose your site and you want that volume to come back up on a different site, we're able to do that as well. And then non-disruptive upgrades. You can actually live migrate workloads onto different nodes, do a full node upgrade in place, including Scribe, and reboot that node, bring it back online, move your workloads back, and your workloads suffer zero downtime. And then lastly, which is kind of what we'll be demonstrating today, is efficiency. And this was very important to us. When we started building Scribe about 6 years ago, we kind of saw technologies such as NVMe around the corner. We knew that efficiency was going to be extremely important in the software stack. As hardware gets faster and faster, the majority of the latency in other storage stacks ends up being in the software itself. So we wanted to start off on the correct path there. So, and I think we've done a pretty good job, as you'll see. So what's unique to Scribe within OpenStack? Number one is performance. As I mentioned, software efficiency was important. 6 years ago, we saw the approach being taken by a lot of other software stacks was to use a mid-layer file system. We really believe that that's a significant bottleneck in a storage stack, and we chose a different path, and the performance results will demonstrate that. I/O reactor sharing. One of the components that is, at least in QEMU KVM, you have the I/O threads and you have reactor threads that are processing I/O in the background. And a lot of solutions will use a dedicated reactor for either every VM or every block device. And what you see is at high levels of performance, at high I/O rates, those reactors start to consume a lot of CPU. And what we've learned is that if you're sharing your I/O reactors, you can actually fully saturate even up to 8 NVMe drives on a single core, with appropriate efficiency in your software. And as a result, you end up with much less CPU utilization on a virtualized infrastructure if you have tens or hundreds of VMs running that can share just a few I/O reactor cores. We also have zero copy end-to-end. This is really important with NVMe drives and 100 gig, 200 gig Ethernet. You don't want to be copying data that you don't have to, because that data copying will start to consume a lot of CPU. And then lastly here, we've implemented a vhost block backend. And this is really important for lower latency. One of the things we realized early on is that the I/O thread architecture used by QEMU has around a 50 microsecond, at least on the hardware we're using, a 50 microsecond latency floor where you just cannot do an I/O faster than 50 microseconds from within a virtual machine. vhost solves that problem. Right? vhost has been around a long time for networking stacks. If you're processing millions of packets per second, you want those packets to be going through a vhost data path. And so we've adapted that and used that for vhost block in Scribe. Also, globally sharing the NVMe drives in your cluster, getting the aggregate capacity and aggregate performance is really important, right? You don't want to be, at least prior to this, if you wanted NVMe performance, you'd have to almost do a pass-through approach. And with Scribe, we're able to, at the software-defined storage level, aggregate the NVMe drives from a capacity standpoint and a performance standpoint, and you'll see that in the demo. Additionally, Scribe uses NVMe over Fabrics internally for communicating with NVMe drives on other nodes. We can also consume other NVMe over Fabrics targets. So if you have an NVMe over Fabrics array or other hosts that are exporting drives via NVMe over Fabrics, Scribe can also integrate those into the overall pool of blocks and share those devices. So the hardware that we're going to use today is a 4-node system. These are Intel boards. They're dual socket. Each socket has a 2.2 gigahertz Xeon 12-core. We're also using Mellanox ConnectX-5 cards with 100 gig, a single connected 100 gig fabric. And then each node also has two terabyte Intel P3700s. So 8 total NVMe devices in this cluster. And keep in mind that the P3700, the 2 terabyte version, is spec'd out at about 460K IOPS and is capable of about 2.8 gigabytes per second of bandwidth. So let's take a quick look at a VM running in this environment. And this is just a standard CentOS 2 install. I did a CentOS 2 minimal install. VirtIO drivers, there's nothing special about this VM. I also have FIO installed on it for the purposes of this demo. So I'm going to go ahead and run FIO, and I'll explain some of the parameters here. We're using the libaio engine, which is probably the most efficient asynchronous I/O for when you're talking to the kernel. We're doing the I/O just on dev-VDA, so this is just a virtualized device on Scribe using VirtIO. QDepth 16, random reads of 4K, and we're actually using 24 threads to take full advantage of the multi-queuing that's built into Scribe. And remember, this is on a single block device. So we'll go ahead and kick that off. And so what we're seeing right now is around 1.1 million IOPS on a single block device with utilizing NVMe devices that are each only rated for about 450, 460K IOPS. We're seeing about 4 gigabytes per second here with this 4K test. So what I can also do to demonstrate bandwidth, and before I do that, take a look at these latency numbers. You're seeing everything here is measured in microseconds. In particular, your average latency on this test was about 361 microseconds at 1.1 million IOPS. So let's kick up the block size a bit. I'm going to go back and edit this 4K and change that to a 16K. And start that again. Same, the rest of the parameters being the same, 16 queue depth on 24 queues. IOPS dropped down a bit, about 900,000 IOPS, but if you look now, we're hitting around 14 gigabytes per second, which is faster than 100 gig line rate. And the reason it's faster is because you remember this is kind of a hyper-converged system where we have 2 of those drives local. And for the local drives, Scribe is not using NVMe over fabrics. It's doing direct NVMe to those drives locally. So we're able to, all the local IOs can avoid the 100 gig fabric. So we're able to get a little bit faster than that 100 gig line rate. So I also want to mention CPU consumption. I'm going to go back to the 4K test and bring it up at 1.1 million IOPS again. And I'm going to show you on the host itself, you can configure Scribe to use as many reactor cores as you want. And in this case, we've decided that 8 reactor cores max is what we're going to go with. So you can see this particular host where the VM is running is at about 50% CPU usage. The majority of that CPU being consumed by the VM itself. The yellow and red bars are the VM, the virtualization happening and running that VM and all the 24 queues that FIO is driving, generating all that workload. Scribe itself is consuming 9 cores, and you can see that there. And that's will remain the same regardless of the number of VMs running on this host. And so you can see plenty of CPU headroom remaining here. But additionally, on the remote nodes, there's really no CPU being consumed by Scribe. The only CPU being consumed is by the reactor thread for the NVMe over Fabrics target. And what we're expecting soon is, with the Mellanox ConnectX-5 and ConnectX-6 that support NVMe over Fabrics offload, once that's supported in user space offload, we'll be able to even eliminate that, so there's truly 0 CPU consumption on the target. So going back and looking at some more detailed results here, I want to point out a couple things. This is kind of the single block device performance, right? This is aggregating all of these NVMe devices into a single virtual block device. You're able to hit I/O rates and latencies that you wouldn't be able to hit on a single device using a pass-through technology. Sweet spot here is probably queue depth 12 to 16. You're over 1 million IOPS total, and your latencies are down around between 300 and 400 microseconds. This is a good graph that kind of demonstrates the advantage that you do get from a vhost architecture. The purple line, both purple lines are using Scribe's vhost backend, and the blue line indicates the traditional QEMU data path of the IO thread, the data plane data path. And you can see, and along the horizontal axis here is the number of VMs we're running. So on the very right end, we're running 64 virtual machines. We're peaking out over 1.6 million IOPS with the vhost, but we can't quite get there with IO thread. And more significantly, the latencies are quite a bit different. With vhost, you're between 150 and 160 microseconds of latency, while you're up over 190 with the IO thread back end. Now, the one thing that's not depicted here is the CPU usage. You have to remember, with IO thread, you have an IO thread. Every single VM has its own IO thread running as a reactor, consuming CPU. That goes away with vhost. So you'd have nearly 64 cores worth of extra CPU to run the traditional QEMU model. vhost solves that problem for you, which is why Scribe gives you that advantage with vhost. Additionally, the latency with vhost allows you to get below that latency floor that the IO thread imposes, which becomes really important if you're using Optane media or if you need extremely low latency IO from within a VM. we were able to demonstrate on the Optane drives from Intel, which are 3D crosspoint based, mean latencies as low as 20 microseconds. And even with long tail latencies as low as 62 microseconds at P99.99. So these are extremely responsive virtual devices implemented on top of Optane. And again, this is kind of a graph showing that on the Intel P4800X, this is the 3D crosspoint device, even up to 24 VMs. These are mixed workloads, so we're talking 90-10 read-write mix. The green line at the top here is a 25,000 IOPS per VM. So we have 24 VMs, each is doing 25,000 IOPS. Mean latencies are below 70 microseconds. So we believe that this is unparalleled in any other storage stack for QEMU KVM. So system requirements, we fully support RHEL 7. Most of what we do is based on either Red Hat or CentOS. So this Scribe will install without any issue on RHEL 7, and that's what we're going to support initially. We also support SATA and SAS drives if those need to be utilized in block devices via Linux native AIO. But to get performance numbers like this, obviously you need NVMe or NVMe over Fabrics. All the testing we've done has been on the Intel P3700s and P4800X. So we know those will work, but there's really no reason why other drives shouldn't work. We've also tested exclusively on the Mellanox, RNICs, the ConnectX 3s, 4s, and 5s all work great. The ConnectX 3s at 40 gig, we were bottlenecking early on the 40 gig, so we went right to the 5s, and obviously we're able to get basically line rate at 100 gig as well. So today we do require an RDMA NIC. I think TCP/IP support will be coming soon if you want to run it on 10 gig, but we highly recommend the RDMA NICs because the levels of performance that you can see and then getting that latency down is really important, especially getting the zero copy from end to end really helps you out. So that's it. We are in booth C12. If anyone has any questions or wants to dive in a little bit deeper, we're here all week. And thanks for your time.